Hi, my name is Griffin Rice, and this is my report for Lab 4 circuits. The purpose of this lab is to predict and observe the relationship between voltage, current, resistance, and capacitance demonstrated by basic circuit designs, and compare the actual measurements of these values to the theoretical values we would get from using formulas, specifically the loop rule. Some of the main principles used in this lab are Kirchhoff's law / the loop and node rules, the conservation of energy, the idea of steady state circuits, and Ohm's law. And then the result for this experiment, the actual measurements from the circuit will be slightly off from calculated values due to inaccuracies from rounding, but they will be similar enough to say that the model agrees with the formula. The initial conditions we use in this experiment, we define the system as a circuit and the surroundings as everything's around the circuit. Wire resistance and ammeter resistance, assume those to be negligible, and change in voltage of the capacitor plus the change in voltage of the resistor equals 0 when we assume the electric field of the wire is equal to 0. For part 1, we use a circuit with two 1.5 volt batteries, two resistors, one 47 ohms and 100 ohms, and two ammeters. The prediction that was that current 1 is equal to current 2, which is equal to 0.0204 amps, and the ammeter reading turned out to be 0.02 amps. When one ammeter was replaced with a voltmeter, the other ammeter dropped to 0 amps, and the voltmeter read 3 volts because current equals 0 when the circuit's open, so the only source of voltage was from the batteries. And some of the voltage recorded across the different segments: A to B was 3 volts, B to C is 0, C to D negative 0.96 volts, D to E 0, E to F negative 2.04, F to G 0, and the rest 0. And then the change in total voltage in the circuit should be net 0, and this supports the loop rule. The voltmeter does not alter the circuit because it has a very high resistance and therefore almost no current runs through it, and in the simulated case it's infinite. And also in part 1, we took the same circuit, moved one of the ammeters to be in parallel with the 100 ohm resistor, and we did this, the current increased from 0.02 amps to 0.06 amps, and this is because the current going through the parallel ammeter is not being affected by the 100 ohm resistor. It's not going through it, and therefore the magnitude of the current increases. Some of the resistance readings we got from the observed values, the resistance at the 47 ohm resistor ended up being slightly higher, same with the 100 ohm resistor, and this because the ammeter is only accurate up to 2 decimal places, so the observed values were slightly higher because of that. For part 2, we used a circuit with a 9 volt battery, 10 ohm bulb, a 20 ohm bulb, and a 200 millifarad capacitor. When the battery is connected to the 10 ohm bulb and the capacitor in series, the bulb initially produced light and then it dimmed until eventually going out, which was due to the capacitor charging. And when this happens, current decreases exponentially to 0. And then when we disconnected the battery, the same thing happened, but the current flowed in the opposite direction because of the discharging capacitor. For the 10 ohm bulb, it took it 13.5 seconds to charge and 14.1 seconds to discharge. For the 20 ohm bulb, it took it 22.5 seconds to charge and 25.1 seconds to discharge. For part 3, we had a 9 volt battery, 200 millifarad capacitor, and a 30 ohm bulb this time. The voltage across the capacitor decreases exponentially as the capacitor discharges. We found using the formula shown, and we were able to manipulate it to equal the natural log of the change in voltage over the change in V naught, made it equal to negative T over RC. And from this we get the slope to be equal to negative 0.1705. RC, our observed RC and our expected RC are both equal to 6 seconds. All right, some sources of error in this experiment: low precision of the simulated ammeters, and human error in calculating charge and discharge times in part 2, just from starting and stopping the stopwatch. For the first what if question, if the real ammeter was used, you would have to account for its inherent resistance, which would slightly alter the current reading. For the second question, if a real battery was used to charge a real capacitor with no resistors in the circuit, the capacitor would ideally charge instantaneously. However, since all real components have resistance, it would still take time for the capacitor to charge.